All right, so we'll have a look at deflection here, and this is on 880, I think. All right, so this relates to how much a beam would deform when it's loaded, which is something you want to investigate a little bit. All right, so when we did the stuff with the bending stress, we came up with this relationship here that the degree of curvature, which we call kappa, which is how extremely something is curved, is 1 over the radius of curvature. Keep in mind that r is the radius of a circle, rho is the radius of a non-circular curve, and that's equal to m over EI. All right, now, if you're in, when you get to differential equations, as should it be intuitively obvious, 1 over rho is from Euler's equation, the second derivative of y with respect to x over 1 plus the first derivative squared to the 3/2 power. Any questions? Yeah, I didn't think so. Okay, very good. Which for us is approximately equal to the second derivative of y with respect to x. So what we're doing there, that's Euler's equation. I'm being a little facetious here, but that's something called Euler's equation, and I don't know, we could reference that perhaps if we wanted to, but I don't really know if I want to. It'd take a lot of time, so we'll just take that one on faith, okay? Now, for our beams, we don't have extreme slopes, so that 1 plus first derivative squared to the 3/2 power, I think, is pretty much going to 1 for a beam that we're going to be dealing with. So that's why that denominator goes away. So we just get 1 over rho is pretty much equal to the second derivative of y with respect to x, which is kind of an important part of this deflection stuff. Okay, and that's again, it's called Euler's equation, developed by one of those all-around scientist, mathematician types named Euler. All right, so what we got here is 1 over rho is m over EI, so that means the moment is EI times 1 over rho. Now, what 1 over rho is pretty much equal to the second derivative of y with respect to x. So what that gets us to is right here, the moment is equal to EI times the second derivative of y with respect to x. That's a pretty accurate approximation. So that'll allow us to put together a pretty long chain of relationships here, where if we start with y being the deflection, and if you have a beam, if you have it drawn up in an xy sense, y would be the deflection. So if there's the beam right there on a couple supports, this distance, which would be the deflection, if we've got that drawn up on a xy axis, that would be y, okay? Now, if we take the derivative of y with respect to x, what we get then is slope, right? And if we take the derivative of that again and throw in a term of EI from up above, you see you get to the moment. Take another derivative, you get to shear, because the derivative moment of shear is shear, and then another derivative again, you get to load, okay? So we get that relationship there where we just take derivatives. If we start with y being deflection, we get to slope. Take another derivative and throw in the EI, you get to moment. Take the derivative of that, you get to shear, and take the derivative of that, you get to load, okay? So that's kind of the relationships that are used to get some of the basics of deflection. All right, now, those are derivatives. However, what we can figure out from doing moment equations is moment. So we can walk it back this way is what we're going to do to get to slope and deflection. So we're going to integrate to walk it back, okay? So if you take integrals, you go the other way. So if you take the integral of load, you get shear. The integral of shear, you get moment. We do that in a graphical sense when we draw shear and moment diagrams. Throw in the 1 over EI now and take the integral of moment, you get slope. Take the integral of that, you get deflection. So what we're going to do is we're going to start with our moment equation. We're going to take an integral and get the slope, and then take the integral again and get the deflection. That's one way to do it. Okay. There's other ways to find deflection, but that's one way. So here's kind of an example, and I don't want to get hung up on the numbers here, but here's kind of the deal. See, when we do these shear and moment diagrams, we're doing graphical integration. So if we take the integral, if we apply those basic rules we went over, if we take, get this load diagram here, we can draw up a shear diagram. apply those same basically set of rules again and get from the shear to the moment, well, you can just keep applying those rules here. So you can look at the area under the moment diagram here. That'll be the change in slope. If you realize that when you load a beam up, you start with a pretty extreme slope, you'll have a negative slope there. Then this area will be positive. That'll increase the shear something like that, the slope something like that. Then you'll get still a positive area here, but it will be increasing at a decreasing rate, so that'll flatten out. So you'll get to a slope diagram like that. And then if you apply those rules again to the slope diagram, you can get to the deflection diagram, which is actually a true picture of how the beam would deform. Okay, so if we just look at these changing areas of the slope diagram, realize that you start with a deflection of 0 and end at a deflection of 0 at the supports. Those are kind of your limits of integration, so to speak. You can get to a deflection diagram. Okay? So that's kind of the deal, okay, the idea. You just take integrals. And normally what we do is start at the moment diagram and then integrate twice and get to the deflection. All right. Now to use the integration method, you write moment equations, integrate once to get slope, second time to get deflection. There are places where we have constants of integration that we can use. So if you have a cantilever, both the deformation and the slope at the support are 0. If you have a simply supported beam, the deformation at the supports are 0. Generally, delta max occurs when the slope is 0. That's that basic rule you learn in differential calculus, that the derivative is 0 at a maximum. Okay. Now, generally speaking, what I do, I use these definitions here. Direction, I have positive up. Deflection is delta. Slope is theta. Distributed load is W. Okay, yeah, but I've seen different conventions used in textbooks and different variables used for these things. That's why I'm calling mine out. Those are the ones that I use. Okay. All right, now this can get a little bit involved, as you see on page 890, but let's have a look at this process. That is a problem to find the deformation at the end of that cantilever beam using calculus. So you can see, why this is not always the preferred method, you might say.
That might be my 3 years of engineering education. That might be the single worst pitch I have ever seen.
Yeah, I know what you mean. It's got a lot of calculations on that thing. When you get down to the end of it, you'll see the deformation is I think it's 0.1311. So that's a lot of work to get 13 centimeters of deflection, I think. But let's see how we would do that. Okay. This is one way to do it, and this is kind of the fundamental way. I don't want to hang up too much on this. Okay. We can get lost in the trees, so to speak. I want to focus a little bit more on the forest when we go through these. Now, we are going to find another way that's a little bit easier, too. I'll point that out right away, okay? So, but I do want to go through this because it's the basic sort of method for it. All right, so let's have a look at this. Let's find how far point C will move down after that load is applied. All right, we've got E is 40 gigapascals. That's a given. We've got the beam cross-section, so we can calculate I. So we've got E and I. E is given, I is just bh cubed over 12, 0.2 times 0.3 cubed over 12. What we want to do is find the reactions. So this is on 890, I think. So what we would do to accomplish that would be to go sum of Fy is 0. So RAY minus the value of the distributed load, which is 40 kilonewtons per meter over a 2-meter span. So RAY is 80 kilonewtons, which is 80,000 newtons. Sum of MA then would be the reactive moment at A minus, so we have a reactive moment at A like that. We also have the reactive force that we just found, like so. So the reactive force is 80,000 newtons, and then the reactive moment then would be that MRA, the reactive moment minus 40 kilonewtons per meter over 2 meters. And then the moment arm on that would be 3 plus, we have to get to the centroid of the distributed load, which is half of 2, so that's 3 plus 1 makes 4. That's a clockwise moment, so it's minus. So for the reactive moment, it's 320 kilonewton meters, which is 320,000 newton meters. And those are counterclockwise there. All right, so I've got the reactions now, and I've got I and E. So now what I can do is go ahead and write up shear and moment equations for this thing, okay? So I have to do this in 2 steps, from A to B and then from B to C. One of the issues in doing this is going to be the constants of integration, so I'm going to have to deal with those as I work through this. All right. So what I'm going to do is write up a moment equation that goes from A to B. So I'll start with that. Now that's going to be pretty straightforward because what I've got is I have no loading from A to B. So all I really have are the reactions and the internal shear and moment. So I'll, just as I do when I'm doing moment equations, I'll take a moment about where I cut, which would be right down there. And what I'll have will be the 320,000 minus 320,000, which is the reactive couple there. That's positive, counterclockwise. Then I'm going to have the reactive force, the 80,000 newtons times x, which is the distance it is from the cut. It's negative because it's clockwise. And then I'll have plus MAB. So I can solve for the moment from A to B. It's 80,000 x minus 320,000. Okay. So that's the moment between A and B. Now, to find the slope. Now, one thing I'll point out here, and you should remember, is even though I was given this stuff in kilonewtons and centimeters, I want to use standard units when I'm doing this stuff. So standard units in the metric system are newtons and meters. And in the English system, very importantly, are feet and pounds. Because we get, it's not feet, I'm sorry, inches and pounds is what we want. Because all of our beam dimensions are in inches. So when we get the moments, we want to convert them into inch pounds immediately, okay? Don't try to start, especially when you're doing English problems, don't try to mix pound feet with inch dimensions and stuff. It just turns into a mess. So get everything into pounds and inches if you're in English. Everything into newtons and meters if you're doing metric, okay? All right, now these are just polynomial integrals, so they're not that big of a deal. They're indefinite integrals also, so we treat them that way. So we got MAB is 80,000 x minus 320,000. So the slope, which is pretty much the same thing as an angle in radians. For small angles, that's the same thing. The slope and the angle in radians are pretty much equivalent. We throw in that 1 over EI term, and then we just integrate m dx. So I got 1 over EI, 80,000 x minus 320,000 dx. So I just integrate it. Now, I don't put the numbers in for E and I until I'm pretty much done, okay? Because they just muck things up a little bit, make it harder to do. So I usually just save those, just keep them outside as a constant. I'll get to them later. That's usually how I handle that. All right, so I'm going to integrate 80,000 x, and that's 40,000 x squared, just a polynomial integration. And I'll integrate 320,000 and get 320,000 x. Now I pick up a constant of integration, which is kind of an issue, but we'll get to that later, and that's plus C1. Okay, now that's the slope. And I just leave the 1 over EI out front, is what I do. Now delta is 1 over EI times the integral of the slope, and so that's the integral of 40,000 x squared minus 320,000 x plus C1, so that becomes 13,333 x cubed minus 160,000 x squared plus C1x plus C2. So that's delta. So now I've got my equations for the slope and delta that hold between A and B. Okay, easy enough. So we good with that? Just integrate and put the 1 over E out front. It's an indefinite integral, so you pick up constants of integration as you go. So we good with that? Okay. All right, now I want to figure out what's going on at C. So I got to figure out what these constants of integration are. See, because what I'm going to do, I'm going to use this actual value at B and use that as a constant of integration when I go from B to C. B is kind of like the common point that I want to use, okay? So I want to figure out what C1 and 2 are first, okay? Now I can do that because what I know is that at A, point A, where x is 0, both the angle and the delta are 0 because it's a cantilever support. There's no deflection or angle at A. That's a solid support right there, right at A. And that's where x is 0, and I'm evaluating from A to B. So I can figure out what those constants are easy enough. What I do, I just plug in those values for my equations. So I got delta is 13,333x cubed minus 160,000x squared plus C1x plus C2. I have that 1 over EI on the outside. Now I know delta is 0 when x is 0. So I plug in 0 for delta, and I plug in 0 for x. And you see, here's why I like to leave that EI out front, because now I'll just multiply through by EI, and that'll just clear. So what I'll get when I run through that, see, all I've got are zeros on everything. I got 0 as 13,333 times 0 cubed minus 160,000 times 0 squared plus C1 times 0 plus C2. And I've got that 1 over EI, but I can multiply through by EI and clear that. And what I'm going to end up with is just C2 is 0. So that's convenient, okay? C2 is 0. You all with me there? I'm just plugging in known values. When x is 0, delta is 0. Okay? I do the same thing again because I know when x is 0, the slope is also 0. So I'll plug in 0 for the slope, and unfortunately that looks a lot like a theta. That should be a 0 there, okay? 0 is 1 over EI. I'm using the theta equation now, the slope equation, times 40,000 times 0 squared minus 320,000 times 0 plus C1. So C2 is 0, or excuse me, C1 is 0 also. Okay. So by evaluating the known values, that when x is 0, both theta and delta are 0, I got the full equations now. I got the equation for slope, and I got the equation for delta, because I just used those equations above, but now I know that C1 and 2 are 0. Okay? So I can go ahead now and figure out what's going on at B, what the angle or slope is at B, and what delta is at B. I do that by using my new equations where I've evaluated C1 and 2, and I plug in now x equals 3, because that's point B. Right here. So I'm just plugging in x equals 3 into these equations. Now I keep the EI, and I'm just running the EI through this. So when I get the angle at B, the slope, I get negative 600,000 over EI. And when I get delta at point B, I get negative 1,080,000 over EI. Okay? And what I'm doing, I'm just plugging 3 into the theta equation and the delta equation. I want that because that's my common point. I can use that to help me evaluate what's going on from B to C. That's why I'm doing that, okay? So now we can do that all over again, okay? Yeah, it was so much fun. We'll do it again. And we'll go from B to C now, okay? And it's the same sort of deal, you know, it's just, you really gotta, you know, I'm being very conscientious about how I'm writing this out so I don't make errors and all that. So what I'm gonna do is I'm gonna go from B to C now. I'm gonna come up with a moment equation. And this is gonna get a little messier now because I'm in that load that goes from B to C. So I've got the reactions on the left. $80,000 and $320,000, and then I've got a x is my full distance. I've got a hard distance from A to B of 3, so this distance here becomes x minus 3, and then I've got my internal shear and moment put there on the cut. All right, so there you go, and then I've got that little bit of distributed load that acts over the distance of x minus 3. I want a moment equation. Sum of moments about the cut is 0. It's 320,000. The reaction on the left, minus, because it's clockwise, the 80,000 newtons times the distance of x. and then plus the 40,000 newtons per meter over a distance of x minus 3 times a moment arm to the centroid of that load, which would be x minus 3 over 2. Okay? And then plus NBC. A little messier this time. Okay, so I'm going to kind of simplify all that stuff. The way I would do that, I would pull that 1/2 out and make this 20,000 times x minus 3 squared. It's just a simpler way to do it. So take that over 2 thing and pull it out as a 1/2 and multiply the 40,000 by 1/2. So then it'd be 20,000 times a square there, x minus 3 squared. Now x minus 3 squared would be what? X squared minus 6x plus 9. And then you can multiply 20,000 through that, easy enough, okay? So pull that 2 out. It's a common thing that comes up with these things. Pull it out, multiply it by your lead coefficient, and you're left with a square, a binomial square you can evaluate, okay? And I did a bunch of these steps at once just because I didn't want to have, too many pages in this. And then I just solve for MBC. Essentially, I'm taking all this stuff to the other side of the equation, and it becomes, I change the sign on it when I do that, so I can solve for MBC. So I'll get that expression there. So now it's negative 320,000 plus 80,000x, and then I've got that binomial that I've evaluated, the x squared plus 6x, minus 6x, and then plus 9. Then I multiply through that through by 20,000, then take the negative of it because I've taken it to the other side of the equation. So I'm doing all those steps at once. Okay? A bunch of algebra. Then I collect terms, and I get this for my moment equation. Okay. There it is. So the moment from B to C is negative 20,000 x squared plus 200,000 x minus 500,000. Okay, simple enough polynomial once I get to it. Then I integrate it twice. So we good here so far? Integrate it twice. Get once to get to the slope equation, but in the term of 1 over EI times the integral of negative 20,000 x squared plus 200,000 x minus 500,000, and that's dx there. Do the integral, you get negative 6667 x cubed plus 100,000 x squared minus 500,000 x plus C3 now. We got a 1 over EI out in front. Take another integral, we get negative 6667 x cubed plus 100,000 x, we're doing the integral of that. So we take our second integral and we get negative 1667 x4 plus 333 x cubed minus 250,000 x squared plus C3x plus C4. And we still have that 1 over E out in front. Okay. Now we got to evaluate those constants, which is kind of unfortunate because we don't have those nice zeros we can use anymore. What we've got, we use that common information at point B to evaluate the constants. We found what delta B is and what theta B is, okay? So what we do then is we've got our theta equation here. And we know what theta is. It's negative 600,000 over EI. We found that up above when we evaluated our constants from A to B and we plugged 3 in. Okay, so we've already found that. So we know what theta is, or the slope, whatever you want to call it, at point B. We found that earlier. And that's down on the lower left. So the angle theta is negative 600,000 divided by EI. And we're going to equate that then to our equation when we plug in the value of B, which is x equals 3. So I'm plugging in the x equals 3 in here, and I'm setting that equal to what I know the slope is at B. The EI's cancel out, which is good. So I get negative 600,000 is negative 6667 times 3 cubed, which is negative 180,000, plus 100,000, 3 squared, which is 900,000, minus 500,000 times 3, which is negative 1,500,000, plus C3. So I can find what C3 is. It's 180,000. I can solve for that. Okay, oh boy, all right. I can do the same thing now. So now I get my full angle equation from B to C. It's right there. So instead of that C3 now, I know what C3 is. It's 180,000. And you can see now why I like keeping that 1 over EI on the outside. It cancels out so many times. It's just a cleaner way to do it. Okay? I'll plug that in later when I need it. I can do the same thing with delta BC. Okay, at B, x equals 3, and delta from the lower left there when we went from A to B is negative 1,080,000 over EI. So I set that negative 1,080,000 over EI to 1 over EI, and then I take this delta equation and plug 3 in, which is the value at B. Okay, and I evaluate that. And when I do that, and I'm going to cancel out the EI, I get negative 1,080,000 is this collection of numbers here that I got by plugging in x equals 3 up above into the delta equation plus C4. I can solve for C4, it's negative 135,000. So that gets me the full delta equation. All right. So now I've got the delta equation, okay? So delta B from B to C is 1 over EI negative 1667x4 plus 33,333x cubed minus 250,000x squared plus 180,000x minus 135,000. So if I want to know how much that cantilever will deflect downward, I plug in x equals 5 because that is the end of the cantilever. It's 5 meters long. So I've got the equation that goes from B to C. I know at C, x is equal to 3 plus 2, that's 5. So I'll plug in 5, and I get delta. Negative 0.1311 meters, about 13 centimeters. So if I load up that cantilever as shown, and it has the size and E value that I show, that point C should sag down 13 centimeters, which is what, 5 inches? Okay. So there you go. Now that's the fundamental way to do it. It's a lot of work, obviously, okay? So there's other ways. Now, but that is, I just want to go through that because that's the fundamental relationship. You take the moment equation, you integrate it once to get slope, a second time to get deflection. Unfortunately, when you do that, you pick up constants of integration, which you have to evaluate. Then you plug in, after you get all that worked out, you plug in whatever your x is, you can figure out what the deflection and slope would be at a given point. Okay. All right, so that's the basic method. Now, as it turns out, there have been people who have done this for standard beam configurations. And I'm projecting those right now. They're available on Moodle, and I will hand those out here so you have them. All right, so these deflection tables are available in Moodle. You will notice one very important thing, or two important things. One is that, this is draft. And the other is that I don't guarantee these are perfectly accurate, okay? So you want to design something, you go to a strengths book and get the tables out of there. I'm pretty sure these are pretty good, but all the same, you know, these you can go to an actual book if you want, you know, really reliable stuff. So what these have are common situations for loadings, okay? So, and now one important thing here is there are two sides to this table. The first side that I'm showing here is simply supported, and then the second side are cantilevers. So just be sure, you know, when you're going to use these, that you're on the proper side. You know, that's very important, okay? And then you just got some standard loadings. Simply supported with a load in the middle. Simply supported with a load not in the middle. Simply supported with a rectangular distributed load. Simply supported with a distributed load over part of it, rectangular. Triangular load, and then a couple. Okay, so those are just common things that come up. So at the basic level, the application of these things is pretty straightforward. Okay, so let's look at one of these, just a simple one. Now there's also a little bit more advanced application of these that you might have to use. But let's start with just a straightforward example. All right, so there we go. We've got a cantilever, 3 kips per foot, 4 kips load on the end, 8 feet long. The beam cross-section is shown. It's 4 inches by 6 inches. So those are true measurements. Of course, you all know that a 2 by 6 isn't really 2 by 6, is it? I mean, for standard lumber, right? So, that's a nominal size. These are true measurements, so we'll go with these, 4 by 6. So 4 by 6 cubed over 12, 72 inches to the 4. We've got E, which is 29 times 10 to the 6. All right. Now, we want to find the angle and deformation at B. So we got to make conversions at first, okay? And I would really recommend that you do these right off the bat. In English, you want inches and pounds. That's what you want. And it can affect a lot of things. So, be a little careful with it. So we got 4 kips there. That's 4,000 pounds at the end. We've got 8 feet. Well, that's 12 inches per foot. That's 96 inches. And then we've got 3 kips per foot. Well, that's 3,000 pounds per foot, but a foot is 12 inches. So that's 250 pounds per inch. So remember to convert everything into pounds and inches. And I mean everything too, okay? Because it's real easy, especially on those distributed loads, to forget to do that because we're so used to seeing pounds per foot or kips per foot. But that's got to be per inch to match everything else, okay? So, just remember to get everything into pounds and inches. All right, now inches are the way to go because you've got E and I. E is in pounds per square inch, and I is in inches to the 4. So that's why we want our length units in inches, okay? All right, now what we're going to do here, we're just going to go to the cantilever table, and we're going to look at that. And if you look at the cantilever table, it's not, really super complicated there. We've got one case that's for a distributed load on a cantilever, and then we've got another case that's for a cantilever with a load at the end. It's the first one and the third one. And what we do here, we use something that I think is named a little bit fancier than it is. It's called the principle of superposition. And all it really means is you just take the 2 cases, figure out independently what the delta and theta are for them and add them up. That's really what it says. The thing is that they're saying there's no real fancy interactions between the distributed load and the load on the end. They just act independently of each other, and you just add them up to get the total. That's all that means, okay? So it's no big deal. All right, so if you look at your table, you're going to see for a cantilever load, you've got the theta, which again, that's an angle, but for small angles in radians, they're pretty much, if you realize those are in radians, a small angle in radians is equivalent to the slope. So that's the slope. It's WL3 over 6EI, and delta B is WL4 over 8EI. That's for a distributed load. And then for a cantilever, the slope there at the end would be PL squared over 2EI for the point load at the end, and delta would be PL cubed over 3EI. Okay. So those are the cases that we're going to use. And we're just going to calculate them and add them up. That's really all you have to do. So obviously this is just, at its basic level anyway, it's just so much simpler than integrating. Okay. So we have to do a fair amount of calcs here though. So I just went ahead and calculated each one separately for the angle. So I've got, what I'm doing here, I'm saying the slope at B will be negative WL cubed over 6EI minus PL squared over 2EI, right? Is that PL squared? Yeah, okay. Now I had to put the negative in, and to see that, I had to realize, well, I'm pushing down on this beam, so it'll bend down, so that'll be a negative slope. So it's up to me to put in the sign on these. And you get into cases where one thing might cause a different sign than the other, so you do have to kind of look at it carefully as far as signs go, okay? So both slopes are going to be negative, both on account of the distributed load and the point load at the end. So I just plug in the values once I've got that. So minus 250 pounds per inch, that's W, times the 96-inch length cubed over 6, divided by E, which is 29 times 10 to the 6, and I, which is 72. And then I just subtract off also the the slope for the load at the end, which is minus 4,000 pounds times 96 inches squared, and divided by 2, divided by E, divided by I. And when I do that, I get negative, and add them together, I get negative 0.0265 radians, which is negative 1.52 degrees. Okay. So if I apply that load to that cantilever, it's going to be sloping down at about 1.5 degrees at the end. So if that's a porch, you know, that's overhanging from the second story of a building, you're going to have to look at that and say, okay, if the people on the end of that porch are kind of tipping over 1.5 degrees, you know, how are they going to feel about that? You know, are they going to notice it? Are they not? You know, that kind of thing, you know. All right, so we're good with that? So pretty straightforward. You just find the two cases independent of each other and add the results. That's all you got to do. All right. So we're good with that? Okay. Again, a little bit of calculation, so you're not going to do plug everything in and do all the squares and the cubes and all that, but you know, fairly straightforward concept. It's the same concept with the delta. You just find the deltas independently and add the results. That's all you do. Okay. Now tomorrow we'll get into more complex applications of this, but there's the delta. All right, so minus WL4 over 8EI, which is for the distributed load, minus PL3 over 3EI. That's the point load. Plug the stuff in, run the numbers. You know, if I were to do this again, I might have just factored the EI out. You know, I might have done that because it might have been a little simpler, but, you know, whatever, it's not a big deal. So that's going to come out to be, when you work it all out, negative 1.83 inches. So you can see why, you know, why you want everything in inches there. It just comes right out then. And you want to catch that early. You don't want to start, you know, if you put the length in there in feet, you'd have feet to the 4 divided by inches to the 3 on the, or inches, you know, you'd have a bit of a mix of units because you start taking things to powers very commonly with this stuff. So again, right at the very beginning, get everything in pounds and inches. Don't try and fix it after you plug everything in. Okay? So this one comes out to be negative 1.83 inches. So again, you're going to have to figure out if that's going to bother people, you know, tipping down a couple inches. You know, and also, you know, at a more, you know, functional level, if you got equipment, like if you're a mechanical engineer, you got moving equipment, you really got to start looking at deltas, you know, for interference and stuff like that. Okay. All right. I'll give you a couple of these. These will be due at the final. Now, I'm going to schedule the final during our Tuesday time because a lot of people have a large number of finals on Monday, and I don't want to put mine on Monday too. So I'll schedule it for Tuesday from 2:30 to 4:30. Okay. Now, if that's a problem for anybody, just let me know. You know, we'll fix it. I know some of you, especially distance ed students, that might be a problem. You know, just let me know, and we'll figure out something that'll work if that won't work for you. Okay. All right. So I would like you to do one of these using calculus. Okay. You might see that again. I don't know. So 403. That's the one that uses calculus. Now these will be due with the final because I can't go over them and get them assigned and graded and back to you before the final. So that'll be one, and then we'll have another here about 411. And so these will be due Tuesday, a week from today. Okay. Now on the final, I'll probably give you a deformation problem, but it will be done with the tables. You know, don't even think about trying to do these at integrals. I've had a couple people try and do that over the years. It's not. Don't do that. Okay. Okay. Just don't. All right, and I'll give you a table, you know, on the final, so that's no problem. Okay. Yeah, I know. Sometimes people think I'm being really nice and friendly by doing that, but what they don't understand is I have to grade it too, so I'm not going there. No, thank you. So that's good for all of us. It's, so anyway, so that's the 17th. I think, okay? And there'll be a couple more that I'll put on those tomorrow. We'll go over more of this tomorrow. Okay.